Hello everyone. So in this video, we will talk about multiple linear regression. So we have just finished simple linear regression where we analyzed the relationship between a single x and a single y. Okay, so it was something like this. Y is equal to beta 0 plus beta 1 times x, right? A single independent variable. So this is independent, and this is the dependent variable or the response variable. It's dependent on the value of x, right? So remember, this is just like, so if you think of this as the weight, right, and the height, okay. So it turns out that, well, at each height value, you have a different distribution, okay? And using this line, you're trying to find the mean of the distribution. And where does the variance comes from? It comes from the, remember, epsilon. Right? So this is the normal random variable with zero mean and sigma square variance. And in fact, this is the what we call the mu of y given some value x. So this is mu y given x. So it turns out that the mu, okay, the expected value changes with different values of x, right? And what we do is we just estimate these values using B0 and B1. We just used SSC, remember, and what was SSC? It was very simple. We just sum all of the deviations around the mean, okay? And the mean is not y bar anymore, it's y hat, because well, the mean depends on x, and we just define it by a line, which is b0 plus b1 x, right? Squared. So what we do is we just find the minimum of this let's say error term, sum of squared errors, by using b0 and b1. So in many applications, well, we just study a relation between one dependent, one y, and many dependent variables, okay, x1, x2, dot, 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 xk. So this is possible through a multiple regression model. So again, if the model is linear in coefficients, we have a multiple linear regression model. If it is not linear in coefficients, remember, we were using the transformations. Okay? So for k independent variables, the model has this form, okay? Beta 0, beta 1 x1, beta 2 x2, dot, 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 beta k xk. So this is our model. One catch here is that, well, since in the previous simple linear regression model, the general notation is y is equal to beta 0 plus beta 1x, right? And if you're just using points, then you say yi is equal to beta 0 plus beta 1 xi, right, plus epsilon I. So for example, you can just say y3 is equal to beta 0 plus beta 1 x3, because this one is the corresponding value for y3, plus this is the error term for y3. But now, well, we have different x's, which means we will need different indices here. So what we'll do is we will just show, for example, we will say y, let's say yj, okay, equal to beta 0 plus beta 1 x1 j, okay, x2 j, xkj, and epsilon j. Okay, that's because in the previous one, we just have a single x value. Okay, so we don't need x1, x2, and so on and so forth. But here we need different x values. Okay, well, this is our regression line, right? And this is the estimated regression line. So I have B0 for beta 0, B1 for beta 1, B2 for beta 2, BK for beta K. Okay. So, so this is what we have. Well, there is a special case of the multiple regression model, which we call the polynomial regression. Okay, So here, in fact, there is only one dependent variable, but the relation between the independent and the variable dependent involves the powers of that independent variable. Okay? So you may have something like this. Y is equal to beta 0 plus beta 1x, beta 2x squared, beta 3x cubed, and beta r x to the power r. Okay? So y is related with different powers of x. So again, the estimated regression line will be something like this: b0 plus b1x, b2x squared, dot, 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 brx. Okay. Well, this is still linear. Why? Because it's linear in terms of the coefficients. Okay? So in terms of the coefficient. But if you have something like b1 to the power x to the power b2, okay, b2x squared to the power b0, if you have something like this, then this is not linear. Okay, so this is not linear. But here the model is linear in terms of the coefficients. So what you can do is you can just find the fit regression line to this model. So in fact, we have seen an example before. Remember, we were talking about testing whether H0 B1 is equal to 0 versus B1 is not equal to 0. And we say that if you are able to reject the hypothesis, it means that, well, there is a linear term in the regression function. Okay, and we just gave this example. So just look at this one. So expected value of y is equal to, okay, so this is again mu y given x. So beta 0 plus beta 1x plus beta 2x squared. So it increases with a linear term x, and it decreases with the square term, the quadratic term of x, right? So what you can do is you can just fit a regression line, a multiple linear regression using this beta 0, beta 1x, and beta 2x. So this is just like your, let's say, first x, and this is just like your second x. Okay. Okay, so what I will do is, before getting into the details of the notation and the hypothesis tests and so on and so forth, let's make an example. Okay, so I think it will be much more clear when we see over an example and then give the definitions about the multiple linear regression. So, well, this is an example in the book, but I just changed the wording of the example. So the like rate, okay, which is y in percent of a meal, is thought to change with three ingredients, okay, measured by the weight of the variables. Well, first meat, the second is vegetables, just like tomato, potato, etc., and spices. Okay. So by just looking at the percent of the ingredients, so for example, 5% meat, 5% of the food is meat, so 20% of the food is vegetables, and I don't know, 3% of the meal is spices. Okay? So when you have this thing, then you have the like rate. So what you do is you just ask the people who just eat this, and it turns out that you have a like rate. For example, 28% of the people just like the meat. Okay. So the study effect of the various concentrations of the three materials on the food like rate. An experiment was conducted with various combinations of concentrations of the three materials related to the response by this model. Okay, so you say that, well, the like rate of the food is equal to beta 0 plus beta 1x1, beta 2x2, and beta 3x2. Okay, so what we think is that, well, the like rate changes linearly with the meat rate, with the let's say vegetable rate, and with the spices rate. So if betas are positive, it means that as x increases, then y increases as well. But we might get a negative beta as well. So for example, if you just increase the rate of the spices, then, well, people may not like it, just depending on the nationality of the people. So this is our data, right? So 1.74% of the food is meat, 5.30% is vegetables, and 10% is spice. Okay? So the like rate is 25.5. And let's look at this one. 10% is meat, right? And 8% is spice, and 4% is vegetables, And it turns out that, well, the like rate is 38.4. Okay. Well, okay. So what you do is just we did it in R. So remember, we in R we have linear models y tilde x. This was for simple linear regression. We will do the same thing, ln y tilde x1 plus x2 plus x3. This is what we will write in the R, or we will just click in the uh, in the data tab. Okay, we just click in the data tab in Excel and just say, well, just make a linear regression and put these values to there to just get an output. And this is the summary of output from Excel. Okay, so we will have similar results from R. So this is what we have, right? Well, just look at this one. This is the R square. Okay, remember our R square? R square was the measure of variability that is explained by the model. So for this model, which model is that again? Y is equal to beta 0 plus beta 1x 1, beta 2x2, beta 3x3, right? For this model, it turns out that the R square is 0.91. We will see the adjusted R square later and multiple R square later, multiple R later, sorry. And well, the standard error, this is the standard that this is what, this is S, right? Or the MSE, right? Right? Not MSE, but this is square root of MSE. So just look at here, this is the whatever we got, this come to that. 430, the square root of 430 is 2.07. Okay, and the number of observations, well, we have 13 observations in the previous case. So just look at this one, this is the ANOVA table, right? So just look at here, exactly the same thing we have here. Okay, so another table is the same. So I have first degrees of freedom here. The change is that, well, in the previous case, so the regression sum of squares was, remember, it was 1, right? Here it is 3 because in the previous case, we only have a single x variable or a single beta. But now there are 3 x variables or 3 betas. That's why the degrees of freedom here is 3 for the regression, right? And the total degrees of freedom is 12, which is 13 minus 1. And the remaining degrees of freedom just goes to the residues, right? SS, well, this is the sum of squares. This is SSR, right? This is SSR. This is SSR. This is SSE, right? The residual or the error sum of squares. And this is SS total. And we will see that we have exactly the same form. So SST is, let me just say, SST is equal to SSR plus SSE, right? And SST was, remember what was that? YI minus Y bar. This is the total deviation, okay? The deviation from where? From the average. Just go back. At the very beginning of our lectures, we said that, well, there are two important measures for a random variable. The first one is where is the center, and the second one, well, how much it deviates around the center. Okay, so what we are doing here is, well, try to see how much it deviates around the center. And we just decompose this deviation into two parts. The first one is SSR, which is the deviation around the mean using the fitted one, okay, fitted one, right? Sum. And the deviation around the explained mean by the model. So remember, this is y hat, this is b0 plus b1x, which was or the x bar for at this value of x, right? Which we call as the so expected, not expected value of what? Okay, so this is y hat, right? Okay, this is y. So square, right? Y, this is yi minus y hat, and this is y hat minus y bar. And just put yi here. And exactly the same formula here. Okay, exactly the same formula. So then what is the difference? Because here we have a multiple regression. Here I have the y I hat is b0 plus b1x1 plus b2x2. Okay. In fact, this is x1I, x2I, b3. Okay, let me just erase this part. Let me erase this part so that I just get some space there. b3 x3I, right? So this is why I had. This is what I had. Right? That's the difference. Now my linear regression is I just make it using three variables instead of one. Okay? And this is my SSR. I just sorry. This is my SSR. This is my SSC. Okay. And again, this is our MSC, or not MSC. These are the mean squares. So what we do is just divide this one by this again, divide this one by this, and then divide this one by this. So this is my observed F. Remember, this is my F observed. Okay, and this is a p-value for this. So when you just look at this, well, the ANOVA table just looks like the same, exactly the same. The only thing is that, well, you have different degrees of freedom. Right? And now, so remember what was, so for the single variable case, our H0 was whether beta 1 is equal to 0 versus beta 1 is not equal to 0. Right? Now, in this case, our hypothesis will be, right? We will just go over this in the following slides. B3 is equal to 0. Okay, what does this mean? It means that, well, all of the betas are equal to 0. H1, well, at least sorry, at least one of them is not 0. Okay, at least one of them is not 0. I don't know which one, but I know that, well, at least one of the x variables that affect the value of y. That's the hypothesis test for ANOVA. And look at the results here. Okay, for the table where we have the B0, B1, and so on and so forth. So remember, in the previous case, we only have these two lines because we have B0 and B1, right? This is my B0, this is my B1, okay? But now I have additional variables, B2 and B3, and, well, we have exactly the same thing here. So this is the coefficient, this is B0, 39.16, 1.02, minus 1.86, minus 0.34. Okay, so these are the estimates for beta 0, or the values of B0, B1, B2, and B3. Okay. And these are the standard errors. So what was the standard errors? This is S of B0, remember. This is S of B1. And how about this? This is S of B2, okay? And this is S of B3, right? The standard errors. And these are the t statistics, or these are the t observed values. So so for which hypothesis do we have these observed values? Remember, so the first line was testing whether beta 0 is equal to 0 or not. The second line, well, it was just testing beta 1 is equal to 0 or not. The third line now tests whether beta 2 is equal to 0 or not. And the last line tests whether beta 3 is equal to 0 or not. Okay, or not, or not. Okay, that's great. So again, we will cover this in detail, but so in order to make an analogy with the previous case, with the simple linear regression, I just want to show this. And these are the p-values, okay? These are the p-values. And these are the p-values associated with this t observed, right? It turns out that all of the p-values are 0, which means the hypothesis do not have any credibility, so we can just reject the hypothesis. Well, I can reject the hypothesis regarding this one, but the last one has a high p-value, which means I cannot reject this hypothesis, which means I cannot reject the hypothesis which says that beta 3 is equal to 0. Right? And just look at this. I have the confidence intervals, right? The confidence intervals regarding the coefficients. So it turns out that, well, B0 is between 25, almost 26, and 22.5. And B1 is between 0.58 and 1.45. Okay. So this is positive and this is negative. See this? This is negative. So what does it mean? It means that, well, as x increases, so y decreases. So remember, what was this? This was the vegetables, right? So if you just increase the number of vegetables, then the like rate just goes down. And well, in fact, the estimate is minus 1.86. And the last thing is, well, this is the confidence interval for B3. Well, the confidence interval has 0 in it, okay? So remember, hypothesis testing and confidence intervals, well, they are equivalent. Since 0 is included in the interval, we can say that, well, so you cannot reject the hypothesis which says that beta 3 is equal to 0, right? So as I said, we will see in details as just we move in the slides, but in order to make an analogy, this is what we have when we just compare the outputs of a multiple linear regression with the simple linear regression. So what is our path? So sometimes you may just feel lost when you just read the nodes or slides with the multiple linear regression. Well, what we will do is we will first construct the model. Okay, but we'll just say, okay, y is equal to something like this, beta 1 x1, beta 2 x2, and this is right, x3. Okay, and in fact, construct the model and estimate the parameters. Okay, so let me just check estimate the parameters here. Okay, so again, now I have construct the model and estimate the parameters. Okay, so this is our first step. Okay, first step. So what we do is, okay, just find the independent variables that are related with y. Just write your model like this and assume that this is your model. Assuming that this is your model, just run the, let's say, the required algorithm, let's say, to find the estimates of beta I. So B0 for beta 0, B1 for beta 1, and so on and so forth. Okay, so this is your first step. And then choose the best model. So what does it mean, choose the best model? Now, well, so in the previous one, you only have beta 0 plus beta 1 x1, right? Beta 0 plus beta 1 x1. But here, the thing is that we have several different parameters. And it turns out that, well, although you think that some of the parameters are affecting your y, it may not affect y. Or although you think that, well, x2, for example, in here, x2 affects y linearly, it may affect, let's say, in a quadratic term, so you should just put something like this, okay? So what you will try to do is just choose the best model among the, let's say, among the set of parameters. Is it x1 plus x3 or x1 plus x2, all of the model, or I don't know, none of them. Okay. Then once you choose the best model, check whether your model just satisfies the assumptions. Remember the assumptions? Well, you have an error term. It should be normally distributed with zero mean and constant variance. Okay. You should be checking this. Remember, we talk about the residuals, okay, which are the EI terms, okay, EI terms. We will just plot them and try to see whether the model satisfies the assumptions. After you feel that, okay, the model is fine, then you will just make predictions on YI, okay? So for example, so if I just put this percent meat, this percent potato, and this percent vegetables, and this percent of spice, then what is the estimated like rate of my meal? Okay, so this is what we will make. Then we will put we will just construct confidence intervals, okay, on specific x values, and we will just make prediction intervals on that specific values. Well, this is not kind of a perfect order, okay? It's not a perfectly one, first do this, then second this, three this, four this, and so on and so forth. Okay, so this is a bit intervened. So this has a just drift structure. Okay, so what does this mean? For example, if you just construct the model and estimate the parameters and then try to choose your model, and just choose the best one. Then if you see that well, it doesn't satisfy the assumptions, maybe we'll just go back to step 0, step 2, or just go back to step 1. Okay? So this is not a perfect flow from 1 to 4, but you will have some just go backs, okay, or feedback loops, right? As I said, we will just see them in details as we see these slides coming in.